Okay, I want to go over some coil windings. When you energize them, how that works into electromagnetism, and then how that works into magnetizing things. The direction of spin for north-south, the direction of winding of the coils. So let me show you what I've got and what I'm going to do. I've got an 18-volt DC battery from a drill. The positive is on your left over here. Here's the positive hooked to two coils. Here's the negative. And I have my switch here on the negative side, so I can use it with my right hand. And it doesn't matter which side the switch is on, it just closes the circuit. What I have here is a 12-volt bulb that I'm going to hook in line temporarily here, so that I can show you every time I squeeze the switch, the bulb's going to come on. But I can't leave the bulb in line with the coils when I do these demonstrations because it reduces the voltage. It's a resistor. So there's not enough voltage going through the line when the bulb's in line to make them magnetize or to show a reading on the pole finder, pole identifier. But I'm just showing you, anytime I squeeze the switch over here, I'm getting a connection of the circuit. I'm closing the circuit, okay? And I can hook this up anytime and show you, but like I said, the coils don't energize with enough power to do what I want to show you with the bulb in line. So, okay, so it's working. On the bottom, I have a left-hand wound coil. And on the top, I've got a right-hand wound coil. These are wound in opposite directions. And this doesn't matter how many times you wind the coil back and forth, you know, left 1, 2, 3, 4, 5, 6 times. This is always true, what I'm getting ready to show you. The first thing is, with no core, these are just steel rods I'm going to use as cores. But if I don't put a core in there, and I energize it, I get the power on, but I get no light on the pole finder, nowhere along the coil, on either one, when it's energized. Just because there's no core in there to show, I guess, the rotation of the current. But once I stick a core in both of these, next thing I want to show you is which one is north and south on these two different wound coils. So now I've got the cores inside, and when I energize, and I've lost connection somewhere just now. The south is over here. The north is going to be over there, if you see that. I guess you could see it. North there, south there on the left-hand wound coil. The other right-hand wound coil is going to be the opposite. And over here will be a south, and over here will be a north. Get it in there right. And there's the north. You saw it. So, with the power, the circuit coming in positive, on the left-hand wound coil, the circuit coming in positive shows a north pole. The right-hand wound coil, the circuit coming in positive, shows a south pole, okay? And it's reverse going out. The left-hand wound coil, the circuit going out shows a south pole, and the right-hand wound coil, the circuit going out shows a north pole. This is true no matter what you do with these. And I'm going to show you that by doing this. I'll unhook the juice. I'm going to flip the coils over. I just reversed them, flipped them around, one end for end, if you noticed. Now this ends, that ends over here, this ends over there, and we're going to wind up with the same thing. Maybe you know this, maybe you don't. So now we've flipped our coils, but we're still, this is the left, this is the right wound, and we flipped them, but still, that's the north, that's the south, and then this will be the north. Let me center that better. This will be the north, and this will be the, let me get it back centered. This will be the south, see? So it don't matter which way you flip the coils. On a left-hand wound coil, the positive side is the north. The right-hand wound coil, the positive side is the south. Always. They're rotating in opposite directions, but the positive side is where it reverses. The negative side is reversed. That is your north and south difference in the left and right hand wound coil. Okay, so that part's that. Now I want to move on to something else. I did want to add this though. Since the current's coming in this way and winding towards us, like this, that's why that's the south side, just like a magnet. It's winding that way, so that's why this is south and this is north. This coil is wound the other way, so you turn the wheel that way, so the incoming side is north and the outgoing side is south. That's just the way it works. It's rotating this way on the left-hand coil, left-hand wound coil, and it's rotating this way on a right-hand wound coil, which is the same thing a magnet's doing depending on which end you're looking at. So that's how that works on coils. Now we'll move on. And I guess I could also point out the obvious. The only way I can swap the north and south for these coils, the different wound coils, is to swap my juice. You know, negative over there, positive over here, and these north and south will swap. But that's the same thing as flipping the coils and getting the same reading. You know, no matter which way you go through the coils. The left-hand wound coil, positive end, whatever end it is going to be north. The right-handed wound coil, positive end, whatever end you energize, is going to be south. And negative north, and the other one's negative is going to be south. It's just the way those work, depending on when they're wound, just like a magnet. Now I'll move on. Now what I want to show you is when you put a core inside a coil, but you just put it in part way, when I energize it, it wants to center. Now watch. It'll pull it in. I get it lined up right. And I must be out of connection somewhere. Let me see. My battery may have went down on me. Let me try just one coil. It always pulls it to the center. And it doesn't matter which end you put it on, it pulls it to the center. It doesn't want to hang out the other side like it's going, like the current is going that way, but it will take the core either direction to the center. Okay? That's the same thing that the poles show. There's a pole on the end and nothing all along, and then a pole on the other end. See that? The poles are only on the ends. And the right-hand coil does the same thing. It doesn't matter which side you stick the core out of, it pulls it to the center, whether it's the negative side or the positive side. It always wants to centralize the core in the coil. It doesn't push it with the current and stop. It wants to pull it back to where it's centralized. So I guess the rotation on each end wants to balance itself on the core. And that's that part. And we'll move on again. So just like I showed with the coil, when you energize it with a core in it, a steel core, you get a pole on each end and a dead spot in the center. And a magnet mimics that same thing. When you magnetize it, you get a pole on each end and a dead spot in the center. And then your other pole. The point is, the mimic's there, but why is that dead spot in the middle? Even though the coil's putting energy through, no matter which way it's wound. And why does it do that? And the other thing I wanted to mention was, if I wanted to take a dead, or just a regular piece of steel and magnetize it, I can do it with either one of these coils. It's just when I magnetize it with the left-hand wound coil, it's going to go like that. As the positive comes in, it's going to magnetize it north to south. And if I magnetize it with the right-handed coil, it's going to magnetize it south to north. Yet from the end, the magnet will look like they're both rotating in the same direction, but depends on which end you're looking at. And these will be the same way. They look like they're rotating in the same direction if you switch ends, but they don't on a coil. The left hand's always the left hand, the right hand's always the right hand. They are different. When you look at either end of this one, it always looks like it's going one way, This one always looks like it's going the opposite way. No matter which end you look at, these two are opposing each other. The magnet will go this way here and that way there, which is the same thing. But it's one piece, and it has both poles after it's pulled out of there. But there's a reason they both have that dead spot in the middle. That's my concern, is if there's a dead spot there, why does it have so much energy to only pull on the ends? The middle has nothing. The BB will fall to my hand. If I put this little BB, which it sticks to the end, can't even throw it off, but if I put it in the middle of the magnet, it just falls to my hand. There is no power there until it gets to the end. So I want to go through a couple other things with some pictures and maybe a little video thing to show you what I think is going on, why it's dead in the middle. But there is a field all the way along it. We can see on a TV screen there is rotation, but it's not enough to do anything to a piece of steel in the middle, only on the ends. And it will stick on the end, but it wants to pull it to the center. And we'll move on to that. Okay, what I have here is just a glass flask. It's square, kind of rounded up here. It was a bottle I found. I've got a cork in the top, just some salt water. But inside I've got some ferrofluid. You can see where it's stained it in a few places. This isn't perfect, but it's got a couple of clear sides where I can show you. So we know, the magnet pulls ferrofluid, but what I want to show you is it always pulls it to it. Look at that, just like metal shavings. Always pulls it to it. It'll go back over there and comes to it. And I'm going to show you more in a minute. If I pull it away, it just goes to a blob, and it always goes to it. And I can, hold it upside down, do whatever I wish, put it wherever I want inside that glass, just like metal filings, right? And you can see, it makes the little cones, if you see them. Yes, you can see them, okay? And the closer you get, the more of them there are. But it pulls it to it. Keep this in mind. The fluid's in there, but the magnetic field pulls it to it, okay? There's an energy there, and it's not pushing away to make them cones, okay? So since you've seen that, and you've probably seen this on other videos, and there's just all kinds of things you can do with it. Hold it way up here, whatever. Do it from the bottom. You can see that the blob just follows the magnetic field wherever I take it. But anyway, I wanted you to see that before we move on to the next thing, and we'll do that. Okay, what I've got here is some ferrofluid and a little cap, okay? And I've got a neodymium magnet. I'm going to try and get it where you can see it. A 1 inch by 1 inch cylindrical magnet. But what I want to show you is watch the fluid, and you see the little spikes coming up as they do. You get 1 or 2, 1, 4, what was that, 7, 4 centers. You get 7. There's 6 around the outside and 1 in the center. I want you to remember that. 6 around the outside and 1 in the center. So definitely remember that for some future videos I'm going to show. Very important. And you come in closer. They keep multiplying. I'm not going to count them. You can see. They just keep multiplying and getting smaller. If you see that, they keep getting smaller. All the little vortexes get smaller. But what I want you to think of is this. Instead of the magnetic field being the cones, the magnetic field is between the cones. The cones are pulled up because the magnetic field is pulling into the magnet, forcing the cones to go between the vortexes going into the magnet. So that's the only reason it would push it up. There's something pulling in, and I'll show you that in just a moment. Just like I showed with the magnet itself and the electromagnets, it always pulls towards itself. Electromagnet or magnet, right? Pulls steel or anything ferrous, and that's what ferrofluid is ferrous. So there's something pulling towards the magnet, and it's not making them spikes go out because of the magnetic field is pushing them out. The magnetic field is pulling in between the spikes. We're looking at this wrong. We're seeing the residual accelerated or pulled towards the magnet is the cones. That's what we're seeing, is where there is no magnetic field. If you understand me, we're looking at this wrong. It's what you don't see is the magnetic field. It is the area between the cones. Okay? No, I pulled the magnet down, just fluid. As I come up, there's 1, 4, and there's our 6. See? If I go down, I can get 5, 4, 5, 6, and then that 7th one. 4, 5, and then it'll go 7. So there's always 6 around right there. And that's, like I said, that's important. Don't forget that. But what we're looking at, the cones of the ferrofluid are not the actual magnetic field. That is the residual. That is where the magnetic field's not pulling down into the magnet. Where it's pulling down into the magnet is what's causing the cones. The vortices, the multiple vortices going into the magnet is what causes that. And it's going around. If you get one cone, it's going around that cone, pulling down. If you see, look at the depression around that cone. There's a depression around the cone. It's pulling down. That is one vortices around that cone, that the cone is sticking up inside the vortice of the magnet. They're reverse. It's pushing it up inside the tornado. And as you come up, there's more tornadoes. As you get closer, there's more and more. They multiply. The closer you get to the magnet, just like this, I'm almost touching the fluid. That's how many there are near the magnet. I'm touching, right now, it's touching the fluid. I'm not even holding the magnet. It's holding itself up against the fluid. That's how many vortices in between those cones that the dielectric is going into the magnet, feeding it. You see that? All the fluid's pulled away from the cap to the magnet, but it's in between them, and it can't pull them all at the same time, and that's why you get cones, is because the shape of the magnetic field going into the magnet is reverse cone shaped of what we're seeing here. Okay? This is my hypotheses on it. Okay, as I've showed before, as I just showed earlier, right here, if you magnetize a piece of steel, a coil wound in a right-hand winding, you're always magnetizing south to north. No matter which end of the coil you energize, the positive end is the south, the negative out is the north, and on a left-hand wound coil, it's reversed. The positive end is the north, the negative out is the south. And then, like I also showed, if you look at either end of either coil, the positive end is going to look like it's going the way the current's going in it. Right-hand wound coil is going to look like a right-hand wound spiral. But if you look at it from the other end, it's going to look left-handed as the current comes at you. And the left-hand wound coil is the opposite. But the problem is, with that, is even though it's coming at you with a left-hand wound, out of this right-hand wound coil, it's coming in right-hand wound, going out looking left-hand wound, but the magnetic field doesn't shoot out in a left-hand spiral. I mean, it does, but what I think happens is, wherever positive's going in, the coil is winding that way, but the ether is spiraling inside the steel in that same direction. Then, when the coil ends on the other end, and comes out, the ether is spun up in that same direction, but I think it goes back into steel inside the coil to meet the incoming. That's why you wind up with a magnet when it's said and done, and the steel is magnetized without a coil around it anymore. You have a north and south. Let me show you with this one. That's why the magnet winds up, with the north pulling in and the south pulling in. I believe that both the south is coming in with the steel, with the positive, but the north, I think it turns on itself. It turns in on itself and goes backwards with that same direction of rotation, backwards and meets the other, and that's why there's that inertial plane in the middle where they, even though they're rotating in the same direction, they cancel each other out. That's why there's only a pole on the ends and not in the middle, whether it's in a coil or whether it's just a magnet. There's always that dead spot in the middle. So what I want to show here, similar to why I've got a, let me show you what I've got, and I'll tell you what I'm trying to do. Got a 12-volt battery, a couple hundred cranking amps. I have some wire wound in a right-hand coil. Oh, it's about 8 inches long, and I have a 3/4 inch piece of steel round in there, round rod, and it's probably 10 inches long. And I'm going to energize it with my switch here. It's on the negative side, which it doesn't matter which side the switch is on. It just lets the circuit connector close. But I want you to watch what these two pieces of steel do to the electromagnet. I have no action right now. And when I count to 3, let me move these back so they're not in the way. When I count to 3, watch the two pieces of steel. This one on the north side and this one on the south. They're both going to go in simultaneously, which you probably know. But I'm going to hit the switch here. Ready? 1, 2, 3. They both go in there at the same time, inwards. Just like how the coil pulls the steel core, as it will, or a magnet, when you get ready to magnetize it, pulls it in to center it. It has to have the incoming swirl rotation of the ether inside the steel coming in, and it has to balance it with it coming out, and that's why it moves the steel to the center. But once it's in centralized, and as it does this, I think whatever side the current's coming out, no matter which way you wound it, which way you're magnetizing it, south to north, or with the left-hand coil, north to south, the output side turns on itself in the same spiraling direction and goes back in and meets the incoming inside the steel. And if you hit that with enough power, not only does it do it with this, which this is not enough power to actually permanently magnetize the rod, but watch the steel again, the 2 bars, 1, 2, 3. It pulls it right to it. They're not magnetized now, but it pulls it right to it from both ends. I think on the output end, it turns on itself in the same rotating direction, but it goes back in the steel to meet the incoming side, which is rotating that way also. That's why when you have enough power to magnetize that steel, especially the right kind of steel, like neodymium material, when you're finished, it pulls from both ends inward. And like I showed before, there has to be a reason that the pole identifier knows it's a south, no matter how I put the rotation to it. But if I get behind the sensor, it goes north. Could be rotation, but I think the sensor, if it was turned around the other way, it would actually show the wrong pole. If that sensor was turned the opposite way, it would show the wrong pole. So they have to make sure they get them right. But that's what I'm saying. The output side, no matter which way you magnetize, south to north or north to south, the negative side is spiraling in the same direction as the positive, but it goes into the steel and goes backwards to meet the incoming positive in the steel inside the coil to make the magnet magnetize. Let me know your thoughts.